In this recording, I want to look at what happens when you differentiate the function y equals x to the power x. I'm going to show you a little feature of this that's not very well known to many people and is rather curious. Before doing that, though, I want to remind you of two basic differentiation laws. First of all, the power law. The power law is the law we use for differentiating a constant power of the variable x, something like y equals x to the n. To differentiate this function with n a constant, we pull the n down in front, but then reduce the power by 1. So we get n x to the n minus 1. This is known as the power law. That's usually the first rule for differentiation that anyone learns. The second one I want to remind you about is when we have y an exponential function. We'll take y to be a to the power x, where a is any constant. Here the x is now in the power, or the exponent. And the rule for differentiating is that we get the same function a to the x, but we have to multiply it by its natural log, the log of a. The natural log is the log to base e. Notice that if a was equal to e here, we'd have ln of e, which is 1. And so when we differentiate e to the x, we get e to the x. That's something we're all familiar with, I think. Okay, now let's think about x to the x again. I want to know how to differentiate it. X to the x is a sort of hybrid of the first two functions, isn't it? It's both a power, but it's also a function of an exponential kind, where the x variable is also in the power. So it's a mixture of the two above. One way that we often demonstrate for differentiating this function is to use logarithmic differentiation. Do you remember how that works? When we do logarithmic differentiation, we exploit the fact that dy by dx is the same as y times what you get when you differentiate the natural log of y. So in the case of our function, y equals x to the x, then we have dy by dx is x to the x, that's the y, and then we have to differentiate the natural log of x to the x. And the nice thing about this is that now we've got x to the x inside the natural log, and so we can use the rules of logs, which say that we could pull the power outside. Pulling the power outside gives us x log x, which is just a product. So now we can use the product rule. And we get x to the x, and the product rule says, first of all, differentiate the x, that gives us a 1, and multiply that by the remaining log x. Then leave the x alone and differentiate the log. And the rule for differentiating the log of x is to take 1 over x. And then finally, x times 1 over x is 1, so we can simplify. And we get x to the x into log x plus 1. We could now go back and put that result into our little table above. Let's wipe out the question mark. And here we have x to the x into log x plus 1. That result is a standard result from logarithmic differentiation, but I want to look at it in a different way now that's rather curious. Let's put ourselves in the position of a student who's given this problem and has never seen logarithmic differentiation, and is perhaps not very expert at calculus. Such a student might look at y equals x to the x and say dy by dx, well, it's just a power, so why not bring the power down and we get x to the x minus 1. A very inexperienced student might leave it that way, But someone with a little more savvy might realize that you could then combine those powers and write that as x to the x again. Now, of course, we know that's wrong. But is it so wrong? Let's go back and look at our result. There actually is an x to the x in the differential. So in some way, this differentiation has remembered that there is a power law involved. So what about that other term, x to the x log x? Well, when we differentiate a to the x, we've just learned, or revised rather, that we get log a times a to the x. Suppose we use this rule on x to the x. Then we will get log x times x to the x. It's also wrong. It hasn't taken account of the fact that x is in the power. But look, log x times x to the x is also in our answer. In fact, our answer seems to be a combination of these two wrong pieces. The differentiation has remembered that x is both a power and a base, like a. And when we do the differentiation of x to the x, we actually get the sum of the two results. First of all, we get the x times x to the power x minus 1. That's from the power law. And we get the plus log of a, which now is log of x, times the original function x to the x. And this simplifies to x to the x plus log x to the x, which is x to the x into 1 plus log x. It's really rather neat, isn't it? This function somehow knows that it is both an exponential and a power, and when we differentiate it, the differentiation automatically incorporates the power law and the law for differentiating an exponential. I want to finish there.